Hello everyone, in this video we will be covering the Euler-Lagrange equations. This equation might seem pretty daunting at first, but in reality, for pretty simple cases, it's not that hard to solve. The first, motivation. So, F force equals force, right? We all know what forces are. They're the rate of change of momentum. So, force minus force should equal 0, right? Now, it turns out that momentum equals the partial derivative of kinetic energy minus the potential energy with respect to velocity. And the derivative of momentum with respect to time equals force. And the derivative of kinetic energy with minus the potential energy with respect to x is also equal to the force. Let's prove some of these things. So remember that the kinetic energy is just 1/2 mv squared. Well, the derivative of 1/2 mv squared with respect to velocity is just mv, and the derivative of the potential with respect to velocity is 0, unless our potential is moving, right? So, and of course, the derivative of kinetic energy minus the potential with respect to x is the force. Let's prove that right now. Since the derivative of kinetic energy, 1/2 mv squared, has with respect to x is 0. Here we have minus the derivative of the potential with respect to x, which equals force. That's the I guess, yeah, that's just like, I think like a definition, or like you can derive that somehow. You can so yeah, no, I think that's the definition of the potential energy, the integral of force. So yeah, we get that relation over there. So since these relations hold, right? So remember, since force equals partial over partial x of t minus v, and force equals the rate of change of momentum, which equals this. So force equals d over dt of t of this whole thing of partial over partial v of t minus v. Force minus force equals 0, right? So partial over actually, it doesn't matter which way, but I just prefer it in who cares. So partial over partial t of partial over partial v of t minus v minus partial over partial x of t minus v equals 0. For a shorthand term, let's define v as x dot, where that's just dx over dt, where so x double dot is just second derivative of x with respect to time. X double dot is the third derivative of x with respect to time. A jerk, I think, and so on, right? And we can also define t minus v as L as a shorthand. That would mean that we have d over dt of partial over partial x dots of L minus partial over partial x of L equals 0. And that's the equation that we had at the top. We had just derived the Euler-Lagrange equation from Newtonian mechanics. That's what this equation is. Where L over here is called the Lagrangian. And the Lagrangian is defined as the kinetic energy minus the potential energy. So yeah. So we just derived the equation and haven't really talked about what the equation really means. So what does it mean? Well, the Lagrangian, for Newtonian mechanics, it's the kinetic energy minus the minus the potential energy. It's just a shorthand term for that. And we plug in the Lagrangian into this equation, and from that, we can derive the equations of motion, or like the x coordinates of the particle by like solving this equation over here. And this is just for the one-dimensional case. Generalize this quite easily to multiple dimensions. You just have separate equations for like each coordinate. So yeah, that's called the Euler-Lagrange equation, and we are going to solve it for the gravitational potential case. So like show you it in action. So okay. So the gravitational potential V of x is just mgx, right? You can derive that for taking the integral of the gravitational force, which is just mg. So the Lagrangian is just t minus v, which is just t minus mgx. Remember that t is 1/2 mv squared, or x dot squared. So that minus mgx. Now, we have the Euler-Lagrange equation, which is this. So we just plug in the Lagrangian here, which is just 1/2 mx dot squared minus mgx equals 0. So what now? Well, we can easily see that the partial derivative of the potential with respect to the velocity is going to be 0. The potential does not depend on your velocity. So this is going to be 0 once acted upon by this derivative operator. And this is just going to be mx dot when we apply our derivative. So we have d over dt of mx dot minus partial over partial x of 1/2 mx dot squared minus mgx. Well, this, of course, is going to be 0 once the derivative is applied to it. This is just going to be minus mg, right? Yes. So you have minus this of minus mg. That's just going to be plus mg, which equals 0. So note that mx dot is just the momentum, actually. And now you have the derivative of the momentum with respect to time, which is just going to be mx double dot, or force. So force plus mg equals 0. We can factor out the m, and we divide both sides by m, and we have the x double dot equals minus g, or the acceleration equals minus g. So in derivative terms, in calculus terms, the second derivative of the position equals minus g. And we can actually solve for the position here by taking the double derivative of it. So what's the derivative of minus g? Well, that's just minus gt. Sorry, what's the integral of minus g? That's just minus g t plus a constant c1. Well, what's the integral of that again? Well, that's just going to be minus gt squared 1/2 plus c1 t plus c2. So that equals x of t. Now you ask, what is c1 and c2? We'll just plug in x of 0, the initial position. That's just going to be 0 plus c2, which means that c2 is the initial position, x naught. So what is c1, you ask? Well, the derivative of x of t with respect to t, that's going to be minus gt plus c1. Now, that's just the velocity, right? V of t equals this. So v of 0, the starting velocity, is just going to be c1, which means that c1 is the starting velocity, the initial velocity of our system. Okay, so this means that x of t equals minus 1/2 gt squared plus v naught t plus x naught. This is, of course, a parabola, a parabolic equation. So yeah, we've just derived x of t with Lagrangian mechanics, as it's called. We could find it much faster with Newtonian mechanics. I'll show you right now. You have that F equals ma, which equals mg, ma equals mg, right? So a equals g. So second derivative of x with respect to t equals g. Sorry, a equals minus g equals minus g. So yeah, and we're done. Like, the funny thing is that with Newtonian mechanics, the funny thing is that with Lagrangian mechanics, in this case, you actually end where Newtonian mechanics starts. That's the most hilarious thing, which is why there are these memes of like, oh, using the Lagrangian mechanics to solve like parabolic for solving what are they called, trajectory equations, because like it's really unnecessary. But it's often used in these cases just to show like just to show that it works. Lagrangian mechanics is much more efficient in more complex systems, where doing Newtonian mechanics becomes a bit of a hassle. It causes a bit of havoc as well. So yeah, and that's Lagrangian mechanics for the gravitational well. Also, there's one more thing that I need to talk about: the action. Now, in classical mechanics and like in all mechanics, there's this thing called the action, and the action is defined as the integral of the Lagrangian from t1 to t2. That's the definition of the action. And there's this principle of physics. Like, it's more of a postulate of physics that objects will always take the path where this value, where the action is extremized, which usually means it takes the path where the action has the smallest value or the maximum value, but it's where it's extremized, which it usually just falls into the former category. And this is called the principle of least action. And from this principle, we can actually derive the Euler-Lagrange equation. I'm not going to show the derivation today, but you can derive it from this action, from this principle. And the really cool thing is that for different systems, the action looks different. Like in general relativity, you have the Einstein-Hilbert action. And from that, your Euler-Lagrange equation is pretty much the geodesic equation that you have. In quantum mechanics, your Euler-Lagrange equation is really just the Schrodinger equation. So that's a really cool thing. It's so general. It applies to so many cases. It's like one of the most beautiful equations in physics, in my opinion. Like not this equation, the Euler-Lagrange equation. This is just a definition, right? So yeah. Also, the principle of these actions is basically saying, in more physical terms, that like, if you have like some space-time diagram, you have x and t, it's gonna take a path where like if you like for each moment in time you have some kinetic energy minus some potential, right? And you're basically summing all of those values. So you have like t1 minus v1, t2 minus v2, and there's like an infinite number of in-betweens, and you're just summing all of them. So you have like ti minus vi, and you're summing them. It's a continuous sum, so it's just an integral of t minus v, which is just the action. It's gonna take the path where like objects will always take the path where this like action takes the smallest value. So yeah, that's just like writing it in more like visual terms. Hope that makes sense. So yeah, that's the whole gist of like Lagrangian mechanics. Hope you guys have a great day.